Good afternoon, y'all. I'm William Niven, and I'll be presenting on Multiview computer vision for detecting defects in munitions. So to set the scene a little bit, my project is a little similar to what Alex talked about. I'm looking at defects within munitions, but there's a very low risk tolerance within this munition. So every single example is being hand-checked by a radiographer who's looking at various views and then various image enhancements to see if he can find those defects. So our mission was to try and to deliver our clients a machine learning algorithm that's going to expedite this process and be able to flag rounds that are showing up as particularly anomalous. Skip ahead a little bit. So these are our zones of interest within the billet of our munition. What's important to note here is these three zones have different thresholds for what constitutes a defect. So they need to be handled independently. So for zone A, for example, the width of a crack, the tolerance is a lot lower than for zone C, so we're not going to be able to batch them together into one training model. So after that, obviously you can see there's not a lot of contrast or artifacts that are showing up in the raw image. So we went through a couple of different enhancement techniques that we look to use to try and bring some of these defects to the surface. What you're seeing in zone C there is called an IQI bar. Some may be familiar. It's a radiographical tool used to kind of calibrate the machine and is not relevant to detecting defects for us, but will come relevant later. So going back, here's my model pipeline for the project. So on the far left, what you're seeing is 4 images of the same exact munition taken from 30-degree deflections of each other to try and get a full picture of the entire round. After that, we applied the Wallace filter, which we found to be the most effective enhancement technique to try and bring some of these defects to the surface to all 4 images. Then we're splitting off into zone C and zone A. And as I mentioned before, they have different fault tolerances across zones. And the fact that zone C has a 75% defect rate and zone A only has a sub 2% defect rate is going to modify the approach that we use to try and detect them. So for zone C, where we have a very high defect rate, we're going to use a convolutional neural network on all 4 views of the same munition. The reason we're doing that, we have a lot of examples of what a defective round looks like. So we're going to be able to use heuristic detection and get a good idea of what a crack looks like so we can label these munitions appropriately. Once we get a confidence that a crack is present from each view, we're going to use some sort of aggregation function to give an overall label to the munition, because we're not necessarily labeling each individual view. We're trying to get a label for the entire round. And then for zone A, where we have very few examples, we don't have enough data to try and get a good idea of what like a heuristic for a crack or a defect would look like. So we're going to use anomaly detection. We're going to use an autoencoder, which was talked about in the USNA project as well. Mine is a little bit different. It's called an over-complete autoencoder. So rather than a compression into like a lower dimensional latent space for like easy representation of clusters, this is actually going to expand the dimensionality of our image and actually increase the number of parameters, because these are very, very tiny defects. So we're trying to extract as much data as we can out of this image to try and find the defects. And then we're going to recompress into our original image and then look at the bitwise error between the two before and after putting it through the full autoencoder. And the hope is that if we train this autoencoder on all clean munitions and then put a defective one through it, there's going to be a high degree of loss because the autoencoder hasn't seen an example like this, and then throw a very high reconstruction loss. And again, we're going to use an aggregation function across all 4 of those views to give a label for zone A in this example. So speed through this again. And then these were our results for just a single view for the convolutional neural network. So the x-axis here is the confidence level that a defect is present. And then this top are clean munitions, and the bottom box and whisker plot are defective munitions. So you see there's a lot of overlap between these 2 distributions. Not what we're looking to see. We'd like to see a big overlap between these 2 so we can draw a line right down a certain threshold and say, hey, anything to the right of this we're going to label as defective, and the left as clean. So luckily what we found is that these defects come in pairs, or at least in groups. So if one view has a crack present, there's a pretty high probability that another view of that same munition is also going to have a crack present in the round. So in order to harness that, we looked at a couple different techniques. On the left, what you're seeing is averaging the confidence for all 4 views, and on the right is just taking the maximum confidence across all 4. So, hey, if one of those 4 views has a 90% confidence that there's a crack present, we're going to go ahead and use that as the label for the entire munition for that zone. And again, despite using all 4 views to try and harness some labeling power, we're still seeing a lot of overlap between clean and defective rounds. So we cannot confidently separate between the 2 distributions. So these were our initial results for a single view for the autoencoder, with the x-axis being reconstruction loss. And what will immediately pop out to you is A, clean and defective examples are once again not separated, but there's a very odd bimodal distribution here. So this immediately popped out. I got excited because I thought those were clean and defective examples. And then after labeling, I saw that it's got to be something else. So after a little bit of digging, what we found is the presence of that IQI bar that I mentioned earlier was having a profound impact on my autoencoder's performance. So these occur on every 0 and 90-degree image, so there's no need for an autoencoder detector, but if they needed one, I created an excellent one for them to use. So our hypothesis here is that the IQI's presence allows for like a non-Gaussian space within the zone C of the round. So what you're seeing is on the left of these 2 pairings is the clean or the pre-autoencoder image, and then what the output is. And what the Wallace filter that I mentioned earlier is doing is that there's no real features present. It's just creating Gaussian noise because I'm forcing it to create some level of contrast within the image. And as you can imagine, a learning algorithm is not very good at predicting pure Gaussian noise. So for a lot of this space, it's just guessing. But because the IQI bar is a very clear feature, it is getting that space of the image very correct, and the reconstruction loss is very low for examples that did have an IQI bar. So our solution to this is going to be, hey, we're going to take the views that have an IQI bar and train it on its own autoencoder that's trained on IQI bars, and then one that don't have an IQI bar on one that's trained that doesn't have them, right? So after we put them through their separate models, depending on whether they have an IQI bar present or not, we're then going to sum up the bitwise reconstruction loss for all 4 views and then make a label. So after that, we're summing, so we have even fewer examples of defective munitions. And we're seeing a little bit of separation, but not enough, again, to draw a clear plane between the 2. So in the future, we're looking to try and harness more examples from our manufacturer, and then also a little bit more computing power. Unfortunately, I didn't have access to a dedicated GPU or cloud computing for this data. So the old Dell Latitude tried to do all of this work for the semester. But I'm looking to use better multi-view combination techniques. So if any of you have like good suggestions for that, I'm super open, would be super curious for what you have to say. Thank you. This concludes my brief.
Okay, thanks, William. We have time for one question.
Thanks for presenting, Adam from Los Alamos. So I had a question. You had ICE on, I think, C. Were those individual models for each of the different aspect views?
So they were trained like flatly. So I leveraged my entire training test subset to train that CNN across all 4 views. They weren't trained specifically for 0, 30, 90, and 60.
When you say all 4 views, is that like you concatenated among like a channel?
They weren't concatenated before they went through. They went through each separately on a CNN that was trained on the entire training set. And then once they got their individual confidence levels, that's where I combined the 4 views.
Do you think you may get more information by, instead of separating, combining the views? So it'd be like a higher dimensional image. So you can have information of 0, 30, 60, and 90.
Right, and trying to use them as like tensors or filters and then put them in together. Yeah, we thought about that and talked about it a lot. Unfortunately, given the computing power, this was already taking a long time to train as just like a single or like a 3-dimensional image. So trying to add those tensors would have just gummed up the machine.
Understandable.
But thank you.
Thank you, William.
Yep.